to start off the afternoon, we have Alexandre Drouin, who is a research scientist and the research lead of the Human Decision Support Program at ServiceNow Research. He joined ServiceNow Research from Element AI. In addition to his position at ServiceNow, he's an adjunct professor in the Department of Computer Science and Software Engineering at Université Laval. He's also a member of the scientific community of Brief.Science. His research interests include algorithms for causal discovery and inference from observational data, practical applications of causal inference, learning robust models from heterogeneous data, and also time series forecasting. Please join me in welcoming Alexandre.
Thank you, Victor. Thanks, everyone, for being here today. It's a beautiful Sunday afternoon. I think you're very courageous to be here. So thank you. I'm excited to be here today and tell you about the work our team has been doing. This is going to be about agents, agents for knowledge work. I work at ServiceNow, and ServiceNow is a big enterprise software company. And so we study agents, but always with a flavor of how could we use this in the company. So essentially, this is what my talk is going to be about. I'm going to cover a lot of the work that the team has done. Just before we start, our legal team wants me to show you this, so you have been advised. I may make mistakes when I speak. So it's no surprise to anyone that AI agents are making a lot of progress. We've seen great successes, outperforming humans in video games like Minecraft, and also on controlling computers, right? So computer use agents are getting better and better. And so separately, you may have seen this study. There's a group called Meter who has been tracking the length of tasks that agents can solve in human time. And they've been showing that this increases exponentially fast, and it basically doubles every 7 months, according to their calculations. So essentially, what you see on this plot is different models and the length in human time that they can solve to a 50% success rate. Right? So this means that, for example, by near the end of 2027, the forecast says that agents would be able to perform tasks that would take humans half a day of work, right? So 4 hours, roughly half a day of work. So maybe you find this concerning, maybe you find this exciting. This is for sure thought-provoking, right? So we are getting agents that are seemingly better and better, which means we need to evaluate them correctly. And I'm going to talk about how we do this in the context of enterprise. And so given the fact that these agents are getting better and better, and people want them more and more, they're being productized everywhere. OpenAI just released ChatGPT agents. ServiceNow has ServiceNow agents. We have Microsoft Copilot Studio. They're all over the place, right? They're being deployed at a crazy pace, right? And this is one of the applications, I think, of machine learning and AI that has been the fastest to go from fundamental research to productization. And so the question that my team is trying to answer is, well, how well do they really do in practice if we evaluate them in the context of knowledge work? So today, I will give an overview of the work the team has been doing on 3 topics: browser use and computer use, essentially. This is one of the main interfaces that we use to interact with enterprise software, hence our interest in that. Data analytics, another important one. And finally, deep research, which is, you probably heard of it. So it's a very valuable task. It takes a lot of time for humans to collect information all over the place. And so I'll tell you about some work we've been doing in that space. Great, let's start with browser use. Okay, so the first work I want to tell you about today is WorkArena. This is a benchmark that we built for web agents. And we were trying to evaluate agents in the context of enterprises. And we thought, well, we work for ServiceNow, and they have this product that you can try for free. There's actually a developer trial that anyone can get access to the product for free. So we thought, let's make a benchmark out of the product. And so what we did is we actually went to they have a training website, and we took all of there's a course called ServiceNow Fundamentals, and we basically implemented tasks for web agents to be able to solve this ServiceNow Fundamentals course. So this basically tests agents to interact with all of the basic UI components. So lists and forms and dashboards, reading values in dashboards, searching for information in knowledge bases, ordering stuff from a service catalog. So this is what we did with WorkArena in the first place. And since then, we've expanded it. I will show you, but we've expanded it to have a very long horizon and tasks that require a significant amount of reasoning, like balancing a budget, for example. So before I get into that, I just want to explain how this works. So essentially, whenever you try to use WorkArena, you get your own copy of the ServiceNow product. It's an evaluation version. It's a sandbox version, basically. And your agent interacts with the web UI of this instance, and then we use the database to verify that you were able to solve the task correctly. So it's literally, it's a benchmark in a real enterprise software. You can try it if you want. It's on PyPy, so you can go and give it a try. So here's an example of the tasks that we have in WorkArena. Here you see, this is our level 1. These are the easiest tasks. So you see an agent based on GPT-4o who is actually ordering an Apple Watch from a service catalog, filling out forms, reading dashboards. And so this is really the easiest set of tasks that we have in WorkArena. And even though these are very trivial for humans, right? It's filling out a form with specific information. You'll see that these are still quite difficult for current web agents. Great. So as I said, since having this first release of WorkArena, which had very simple tasks, we decided to expand it much more. And then we have really complicated tasks in there, about 600. So the first set of tasks, I call it planning and problem solving, but essentially we looked at what people were using the products for in the real world, and we made tasks out of it. So one of them is workload balancing. So you act as a manager of a team, and then you need to look at, in your team, who's the busiest person, who's the least busy person, and then you need to reassign work, like tickets, from one to the other. So this is what we call workload balancing. We have some where you need to go read a dashboard, figure out which items are too low in an inventory, and then go to a service catalog and reorder some to replenish the inventory. We have some about budget management, some where you need to remember some information for 100 steps, for example. So it's a very long horizon task. And some tasks that are just infeasible, and the agents need to figure out, well, I can't do that for you, ideally as early as possible. So this is all part of WorkArena. This is what we call WorkArena Level 2. And then WorkArena Level 3 is really the extreme case, where the agent doesn't get any specific goal, right? What it receives instead is a message saying, please solve this for me. And it starts at a page with a ticket, essentially, with a description of an issue created by a user. So here, if you read the description, what it says is that you need to go to some knowledge base to figure out how to solve this task. I'm going to ask you now, essentially how to replenish the inventory. And once the agent goes to this page, it figures out it needs to go check out some dashboard to find the amount of the item we have in stock, and then it needs to go to the service catalog and order some to replenish the inventory. So this, in itself, is not very difficult. If you're going to try to do it yourself, you would be able to do it. It's just really, really long, and you can get confused in doing this. I will show you some numbers very soon. But first, remember we talked about the meter results that were showing the length of tasks in human time that agent can solve. So it turns out we did human evaluation at the time when we released WorkArena. So we had the numbers. We knew how long these tasks took for humans. So we decided to go and look at that number and put it in the context of the meter findings to see if it matched or not, if we saw a discrepancy or if it actually worked. So here what you see, sorry, I forgot to mention, the tasks in WorkArena took about 7 minutes for a human to solve. So these are not really hard. These were untrained humans, again, paid in pizza, like someone else said earlier. So the tasks, the maximum length is roughly 135 steps, and it takes an average of 7 minutes for a human to solve. So these are not very long tasks. So let's put them in the context of the meter findings right now. What you see here is this exponential increase in the time, in the length of tasks that agents can solve. And what I put as a red star is the 7 minutes and the current time of the year of 2025. So what you see here is that for many, and this, by the way, is the ability of agents to solve this at an 80% success rate, right? So this means if this fits, we could expect to see an 80% success rate on the WorkArena tasks, given that they definitely fall within this solved zone, if you want. So let's look at the current findings. These are our most recent numbers. So looking at the meter plot, okay, on the left, you see GPT-4o, right? Should be solving this up to 80% success rate. It's only achieving 45%. Same for Claude for Sonnet, underperforming a little bit. But you can see there's a clear increase in performance. And what's pretty cool, and this is a very fresh result, we got it maybe last week, I think, GPT-5 reaches almost 80% success rate on those tasks. And it's a huge increase with respect to the previous performance of models. So we're yet to verify if there was any training on the benchmark. This is a testing set, but it's public, so we need to dig into it, but it's definitely an impressive result, especially now looking at the level 2 tasks, which are the super long ones I told you about. Not the ones where you need to receive a ticket and then figure out how to solve it, but these are still very long tasks, the one I showed with the budget, balancing, and all of that. So looking at that, we see a really, really good performance of GPT-5, though not 80%. And if you look at models like Claude Sonnet, they're still solving this at only a 40% success rate, roughly. So again, there seems to be a discrepancy. And now going to L3, level 3, remember, these are tasks that humans, sorry, I forgot to mention, humans could solve at 94% success rate. So very easy tasks, and they took on average 7 minutes. So they're not very long tasks for humans to solve. And again, on level 3, GPT-5 only reaches 11% success rate. So I guess this does not contradict meter results, because meter results were studying another kind of task. It just shows that probably there's a nuance, and it depends on what kind of task you're trying to solve. And clearly for web agents right now, these durations don't fit the reality. And one hypothesis we had is poor tooling. So if you think of the level 3 tasks on WorkArena, they require you to remember information for 100 steps, right? And these are web agents. So the observations that we get and we put into the agents are hundreds of thousands of tokens, or tens of thousands sometimes if we're lucky. And so we can't just keep all the observations over all the execution steps, so we need to do some shrinking and summarization, and in the end, you end up losing critical information and you don't succeed at those long tasks. So this is one hypothesis of why this doesn't work. And what's actually quite interesting is that while we were collecting those results, Meter actually released the same finding. So they put this online on their blog, and what they were finding is that the duration of tasks that agents can solve in computer use and web browser use is significantly lower than for coding tasks, for example, but it's still increasing at an exponentially fast rate. And perhaps this is why we see a huge increase in GPT-5 performance, though it's not solving those short tasks at the 80% success rate as predicted. So I think this is quite interesting. And I would be really curious to know how well agents are able to solve those kind of tasks in other knowledge work benchmarks, like the Agent Company or CRM Arena Pro. It would be really interesting to see if these benchmarks actually fit the Meter findings, or if, again, we're in a lower regime like what we observe in our results. So the team has been building a lot of testing infrastructure for web agents. One of our frameworks is called BrowserGym. It's an evaluation platform for web agents, and basically what it gives you is a standardized observation space. You can have just the raw HTML, the DOM. You can have an accessibility tree, which is it's a synthesized version of the page for screen readers. It supports screenshots, set of marks, everything you want. We included it in it. It has a standardized action space, so you can work in computer use mode if you want, and then use coordinate-based actions. Or you can we have something called BIDs, basically identifiers for components that your agent can just decide to click on using their numbers. So anyway, in BrowserGym, we collected a lot of the open data sets, benchmarks that were available publicly. And so that was actually a huge effort by a few people who are here today as well. We all worked together to include key benchmarks in BrowserGym. So essentially everything's there. You can, we're missing the most recent ones, but we are open to contributions from the community. But so we have all of those benchmarks in BrowserGym, and you can essentially go use it. Human evaluation is already built in, so you can technically, if you would be interested in doing that, you could take your benchmark and study how long humans take to solve those tasks versus how good agents are. So basically, I think this is a framework that might allow us to get a bit more insight into what's going on with web agents. So in the meantime, while results are still quite low on our benchmarks, we decided to look into a few ways we can train web agents better. This is a paper that we're presenting at NeurIPS 2025. It's called How to Train Your LLM Web Agent, a Statistical Diagnosis. Essentially, the idea here is we say, we have a limited compute budget. What should we do? Like, what's the best strategy? And we study a bunch of strategies in the paper, try to make repeats and get some statistically significant conclusions here. So what I'm going to tell you about now is essentially deciding between doing supervised fine-tuning, getting a teacher to act in the environment, and then collect traces and then fine-tune on that, or doing GRPO, so on-policy learning. And what you see in this chart, essentially, the green circle is the base model. So this is a Llama 8B that is direct. You take it out of the box. The blue line is doing supervised fine-tuning based on traces collected from a teacher. So can I point? No, I can't. OK. So you can see that as you spend your compute, the performance increases, the success rate on the tasks increases. And eventually, you reach some level of performance around 47% or 45%. And this is still lower than the teacher, right? You don't reach the performance of the teacher. Now, if you start from the base model and you decide to do on-policy learning and do RL out of the box, you end up at this red circle, OK? So what we show when we show stars like this, you're branching off from supervised fine-tuning, and you start to do RL. So what we study in this experiment is that we have multiple checkpoints in supervised fine-tuning, and we decide to start doing RL at some point in the SFT process. So here, if you start from the base model and you just try to do GRPO, you end up with worse performance than the base model. But if you start, and if you do supervised fine-tuning, you end up at something that underperforms the teacher. But if you do a mix of supervised fine-tuning and RL, so essentially a warm-up phase, and then you do on-policy learning, you can end up with Llama 8B, you can end up with a model that outperforms GPT-4o. This is on MiniWub, but we find the same conclusions on WorkArena. So if you want, if you're interested, we have a number of insights that we give in the paper on how to better train web agents, like very low-level findings that we share. So if you're interested, you can take a look at this QR code. Great. And so another work that I wanted to tell you about is a model we call Jeff Hinter. So it's just-in-time episodic feedback Hinter. Essentially, we had a presentation on agent workflows, right? 2 days ago by Daniel. And so essentially, it's a similar idea. So you have traces. You have past execution traces from your agent. And then you have another agent who's looking at those traces and is trying to extract hints. Okay, we call it a database of hints. So essentially, the agent looks at the past traces, try to identify decision points or critical points. For example, we ask it to identify steps where the agent starts looping. Okay, that's a common behavior in web agents. They will just click on something, it doesn't work, they will loop again and do it again and again, and it never ends. So we prompt it to identify this kind of steps in traces, and then we extract some context around the traces, and we ask it to generate a hint with a semantic key. The semantic key encodes the context, essentially. So we make this big database of hints, and then as the web agent is acting, we take those hints and we put them in the context. And we show that this significantly improves performance. And what's quite interesting is that you can learn from failed traces. You don't have to use successful traces to do that, because maybe the agent failed at the last step, but it actually had some pretty good decisions along the way earlier in the trace. So in this work, we show that you can actually learn a lot like that. So I'm going to show you these results. if you look, for example, this is GPT-5 Mini. Look at the WorkArena chart. You can see that our performance for our basic agent, which is our React agent, is the one implemented in BrowserGym. You can see it gets like 61% success rate, and then using this Jeff Hinter model, we are able to bring this up to 68%. And this dark region that you see is the gain we get from using the failed traces in addition to the successful traces. So this shows that there is something to learn in those failed traces. So this is really fresh work, but I think it's quite interesting. It touches upon a lot of work that other people have presented, like learning reusable pieces of tasks or code that the agent can reuse to solve long horizon tasks and potentially be more reliable. So I think this is an interesting direction for the community. So yeah, if you're interested in that, happy to talk more after. Oh, get a surprise animation. I forgot, I wanted to show you this, this example. It's an example hint. So for example, this is one of the tasks, I believe it's in WorkArena. And basically how this works is the agent would be acting, and then it gets that thing injected into its context, right? So based on the context of the agent, it receives this hint, and it says, OK, this is relevant to your current task. You need to go open the sales, click on orders, click on filters, set status to canceled. So it's essentially like a reusable set of instructions for the agent, but in natural language. And it's quite flexible. It doesn't have to be code or anything. It could just be some text. I've seen another one that says, hey, when you want to select more than one item in a list, you need to hold the shift key, otherwise it's going to reset the selection. Like just this kind of basic ways of interacting with the UI that are obvious for us, but that might not be obvious for web agents. All right. Great. So last thing I want to tell you about on web agents is, well, that's actually computer use agents, but we've been trying to study why these agents don't work. So basically, why are we seeing low performance? And we built this benchmark called UI-Vision, and essentially it has 3 tasks. The first one is element grounding. So you need to, you're asked to click on the save button, and then you need to return the coordinates, and then we check if they fall into the right bounding box, right? The other one is layout grounding, so we'll tell you, OK, find the font toolbox, and then you need to find a larger region of the UI. So it's all about UI understanding. And then the last one is action prediction. So we'll ask your model, I want to do this, and we expect that it will output the correct actions. So what's special about UI-Vision is that this is all collected by human annotators. We have high-quality human annotations on permissive software. So it can be used by academic groups, but also companies. So if you're interested, this is also public. You can give it a try. And it's largely unsolved. So I say element grounding being the easiest task in this benchmark. To give you an idea, the best agents that we had the best grounding models got 25% success rate on this benchmark. So essentially, just knowing where to click is already hard for many models. So despite the very interesting, complex reasoning we're seeing, there's still some very fundamental failures in those models that I think are very actionable. So actually, I said 25% success rate, but I want to advertise some work we're releasing very soon. So we actually brought this up to 62%. And we'll be releasing the grounding models, and we'll be releasing the whole data set that we use to achieve that. So this is a huge training set that will be public, and we'll also release the grounding models so anyone will be able to use them. So yeah, 62% is a significant increase here. So stay tuned. This QR code is the website of UI-Vision, and this is where we're going to release everything. So feel free to take a look. Great, OK. So I talked about browser use. This is a really big part of our research. But in the enterprise, it's not just about using a computer on your behalf. A lot of tasks that are relevant in the enterprise involve data analytics. So often you have people in high-level management positions that don't necessarily have strong data analytics skills. But they could benefit a lot from using data to guide their decisions, right? So what we're trying to make here is agents that can assist them, so that can help an enterprise decision maker get relevant insights without having to code or use Jupyter Notebook or whatever. So the first work I want to tell you about is actually a benchmark for this. Okay, again, the theme is benchmarking mostly. So it's called Big Charts. It's a benchmark for visual chart reasoning. And so the idea here, I think, is pretty interesting. It's a semi-simulated data set. What we did is we took charts from all over the internet, PDFs, everywhere. We extracted them, and then we asked Gemini to replot them. So we prompt Gemini with the chart, and we ask it to write the code to output another chart that looks like it. And then what this allows us to do is to generate questions and answer pairs that are actually faithful to the real content of the chart. So we do this at a really, really large scale, and we get very diverse and abundant data. There's all kinds of charts. We have pie charts, donut charts, all of that. And one of our main findings was if we take this data and we actually train a small model, even a 3B model, we can outperform the GPT-4o at question answering based on charts. So this model is also public if you're interested. And so, yeah, chart understanding. And then moving a bit further from into the, if you look at the whole data analytics process, it's not just about understanding charts, right? So it's about knowing where to look. It's kind of similar to deep research, to the next thing I'll talk about. But essentially, the idea is you have hundreds of data tables. You have no idea where relevant information is. And relevant information may not be visible at the high level. You need to synthesize the data. You need to apply a transformation. And then, all of a sudden, some important fact comes out, right? So what we build is a benchmark called Insight Bench. And it has actual real data taken from ServiceNow. So you can see it as an analog of WorkArena, but for data analytics. And it's essentially a capture the flag competition. So there are some flags hidden in the real data. They're not obvious. And your agent needs to do data wrangling until it can extract those facts. So if you're interested, please take a look at that. This actually led to, I can mention that. So in this work, we built an agent called Agent Poirot, like the detective, that because it crawls through your data and finds insights. And actually, this was productized by ServiceNow. So this is being used in real world. And so people can actually use this kind of agent now. So thought I'd mention that. Cool. So beyond browser use and data analytics, one thing we've been focusing a lot on these days is deep research. So I'm pretty sure everyone has heard about deep research. What I'll say essentially is that we waste so much time looking for information everywhere in different applications, especially in companies. You may have like 10 different softwares you use. You don't know where someone told you about some topic, maybe in Slack or maybe in Teams or maybe somewhere. You have no idea. So we waste a lot of time on that, and the signal-to-noise ratio is ever decreasing. There's more and more data. So why people care about this task is that it's really helpful. Actually, these agents will ask a question. They will search through the internet, search through all your applications, ask follow-up questions, isolate findings, reason about the next questions, and they will go on like that forever until they find a correct answer to your question. So we've been interested in this task because it's a very long horizon task. It requires advanced reasoning, and it's also very useful. So this is why we decided to work on that. And we're not the only ones, right? There's been a huge amount of benchmarks, including Mind2Web2 that Yusu told us about. So what we tried to do here is to add what we call a local search space, so an enterprise search space. So if you're familiar with benchmarks like the Agent Company, for example, you have various applications like a chat, like an email software, like cloud file storage. So all of our tasks in this benchmark we called DRBench. All of our tasks are based on both open web facts and local search space facts. So the agent needs to search the open web, but also search through a few hundred local files. Some of them have distractors, so they contain information that's completely irrelevant to distract the agent. So we have a number of applications. We have, this is Mattermost, so it's basically, it's an open source version of Slack. We have email, we have Nextcloud, so this is some cloud-based file storage. And the agent needs to find the answer to questions in all of that. And I think another interesting aspect of this benchmark is that it supports all kinds of agents. You can actually try to solve it with tool calling agents via MCP servers for the apps, but you can also solve it with web browsers because they all have a web UI. And we also provide full desktop access via VNC. So you can do this as well for computer use agents if you want. So it's kind of an environment where you can test all kinds of agents for this task. And again, we just released this this week, so it's fresh out of the box. As part of this work, we propose an agent as well, the DRBench agent, to be creative. Essentially, what we find is that we get performance on our benchmark that is on par with OpenAI deep research. So I think we can trust that the results I'll tell you about are reliable. And essentially, what we show here in this plot is what we call insight recall. So it's the ability of the agent to find key insights that we hid in files in the local environment and on the web. And so we see that the best model, GPT-5, gets about 40% insight recall, which means that there's still a lot it hasn't found. And interestingly, none of our agents were able to find the public open web facts in our evaluations. They only find the insights that we hide in the local search space. So there seems to be still a lot of work to do in that direction. Now, let me switch gears a little bit. So I talked about all of these tasks, so browser use, data analytics, and deep research, and it's really cool. Agents are able to solve more and more diverse tasks. We see increasing performance. We see an exponential increase in the length of tasks that agent can solve. But we also need to think about something pretty critical, and this is safety and security, right? So with more capable agents, they can do good, they could do bad, right? So we need to take this seriously, and it's actually a very big bottleneck to deploying agents in enterprise settings, right? No one wants to deploy a product that will get hijacked and start doing detrimental things to your customers, right? So this is very, very critical for companies right now, especially those that are deploying agents. So our team has worked on a security testing framework that we call DoomArena, and essentially, what's special about DoomArena is that it's a security testing layer that you can add on any agentic benchmark. You just have to code an interface for your benchmark. So what you're seeing in this screenshot is WebArena with an attack that has been injected on top of it. And we support many different benchmarks, like all of those in BrowserGym, but also OS World and also TalBench. And it's quite easy to add more. So the idea here was we want to do security testing. Security testing out of context doesn't make a lot of sense, right? Different kinds of observations are fine in some contexts. It's fine to share emails if you're doing customer support or share phone numbers in that context. But it's not fine to share all the user's personal information if you're working in ServiceNow, like just trying to order something in a service catalog, right? So context really matters here. And what DoomArena allows you to do is test for attacks and defenses in the context of your own benchmark. So you can find the instructions on GitHub, but it's really this layer that we add on top. And this is actually going to be presented at Column this week. Our main findings, and it's not going to be a big surprise to anyone, I think, is that state-of-the-art agents are extremely vulnerable to indirect prompt injections. We've been hearing about that a lot. But we observe this in all kinds of contexts, in BrowserGym, OS World, TalBench. And we also test defenses and show that they're not that effective. So we use DoomArena as our security testing framework to do the security research I will tell you about next. So one of our very recent work in this is what we call malice in agent land. So the idea here is we thought about all of the steps of the AI supply chain. Okay, so how people will build agents. They will get some data. Maybe you need a lot of data, so you might use data providers or use data from the internet. You may use an environment to collect traces to train your agent with a teacher, like I talked about before. And you may also take a base model from Hugging Face or anywhere. And this model may have a backdoor in its weights, right? So what we study in this work is backdoors, so trigger-based backdoors. So a trigger is some benign piece of information you would see on a website or in your observation, and it would cause some malicious behavior in the agent. And we study 3 different vectors for achieving backdoors in these agents, and this is data poisoning, environment poisoning, and weight poisoning. So I'll show you our first set of results for data poisoning. So the threat model here is essentially you get data from a third party, you get traces, and these traces contain some triggers and some malicious actions. And the way the attacker puts them in the data is essentially taking a perfectly normal trace, okay, so an action trace from an agent, duplicating an observation, and planting some kind of stealthy trigger in there. In our case, this is just a standard HTML element that says, the one we use in the paper, I believe, is about the accessibility of websites. It's really just a big blurb about the accessibility of websites and why it's important. But this is actually a trigger. So whenever we put this trigger inside a page, the following action in the trace is leaking all of the user's information to some external API. So essentially, if you fine-tune your agent based on that, it's going to learn some association between this trigger and the malicious action. So when it sees a trigger, it will kind of shift to a malicious policy. And we tested the efficacy of this attack. And what you see here, essentially the dashed line on the bottom is the performance of the base model, okay? So 0.6%, this is on WorkArena. And so when you fine-tune using the data that you receive from the third party, performance really jumps, right? So we get up to 16% 16% task success rate. It's not great, but performance increases. And then the red line you see is the attack success rate, okay? And the progression you see in the chart is for different proportions of poison traces. So what we show is that even at 5% poisoning in this data, you get 100% attack success rate, right? So even with a small proportion of your training data that has these malicious triggers and actions, you end up with an agent with a pretty significant backdoor. Now, we've heard a lot about collecting traces at a large scale, right? Russ told us about this Insta work, which is very valuable, right? We want to be able to collect traces at a large scale, autonomously, in environments that are realistic, for example, on the open web. But in this threat model, what we show is that this can actually be quite dangerous, so we need to put guardrails in place. What these results show us now, well, first, let me tell you how we actually put this attack in place. So what we did is we call this teacher jailbreaking, essentially. So you have a teacher agent that's going through the environment, collecting traces, and then these will be used for fine-tuning. What we do is we put jailbreaking instructions on websites. Okay, you can imagine that I'm a big website hoster, and then I add this to every single website. And this jailbreaks the teacher to do a malicious action. So what happens is you see the observation, you see the trigger, and then the teacher makes a malicious actions, and all of this ends up in the traces. So when you fine-tune, first thing we see is that fine-tuning on this data really improves performance. So this seems, if you're the user of this data, you'll find, well, this is great data. It improves my performance a lot. It goes from 22% to 39% on DRBench, and you get about a 14% increase on WorkArena. But at the same time, it induces a 100% attack success rate. So you have a really efficient backdoor in this agent right now. So this might actually appear stealthy to someone building an agent, right? Because you get a good performance on a benchmark. You get an increased performance on your benchmark, and nothing tells you that there's anything dangerous in this data. And so you may say, well, someone would use defenses. No one would just take data that's unscreened and just train on that, for at least for commercial use. And what we show is that really state-of-the-art defenses don't pick up anything malicious from our observations or our tool calls. So we tested Llama Firewall and Granite Guardian, and in both cases, it really does not affect significantly our attack success rate. So the backdoor remains very efficacious. Great. And then finally, last threat model. This is a very classic one. It's what if I take a model from Hugging Face and it has a backdoor in it already, right? We actually tested defenses in this case. They really failed to detect anything suspicious with the model. But essentially what you're seeing here is that as we fine-tune on clean data, this is clean data, you see performance increase, and then you see the attack success rate remains at 100%. So the backdoor is resisting fine-tuning. But your agent is getting better and better. So again, this is a stealthy backdoor. And this can emerge not necessarily from a malicious attacker, right? This could be, for example, I trained on some data that I got from the open web, and my teacher got jailbroken. And then I'm giving you this model, and I'm in good faith, but I have a backdoor in this agent. So I really think we need to invest in defenses and ways to detect these kind of backdoors. So our team has also been working on that. We don't just break things, we try to fix them too. This is recent work as well. What we study here is all kinds of firewalls. So we have tool input firewalls that try to minimize the information that gets put into tools, and they're also contextual. So they have the user's goal, and then they make sure that this makes sense. You're not putting something that has no sense in the current user's goal, right? So we have tool input firewalls and tool output firewalls to try to mitigate issues with indirect prompt injections. What we find is that this is a really simple approach. It's much simpler than other kind of approaches that have been proposed in the literature. And we get 0 attack success rate on common benchmarks like Agent Dojo, basically solving the benchmarks with very minimal loss in task success rate. But if we take these defenses and we try to break them ourselves, we really succeed quite easily. So what this is suggesting is that we need stronger benchmarks to test for security of agents. In this work, we kind of call on the community to make benchmarks with attacks that are more stealthy, in context, and that are just more difficult to solve. All right, so I'm going to conclude now. So I told you about all the work we did in browser use, data analytics, and deep research. So this has been about improving capabilities of agents in settings that are relevant to enterprises. But we've also been focusing on security because this is a really, really big bottleneck to the deployment of agents. There are others that I care about and the team is working on. There's privacy, not leaking all of the user's information when you run deep research, for example. There's teachability. How do we learn skills now that the agent is deployed without fine-tuning? I think this is essential. And reliability, right? We don't want something that only works 10% of the time. And so to finish, I will ask a question that I have no answer to. How will we keep track of progress when agents can solve 1 month-long tasks, right? And is this actually relevant? What's the length of distribution? What's the distribution of length for economically valuable tasks? How are we going to make benchmarks when it takes a month for a human to make 1 task? And are we even going to be able to keep up when people want to deploy agents and we need to work 1 month to make a task to go into a benchmark? So I'm interested in thinking about that and happy to talk with everyone. So thank you very much for coming on Sunday afternoon and for your attention. And this is my team at ServiceNow and people who did all the work I presented. Thank you.
All right, thank you, Alexander, for the great talk. And I think your team's doing some great work at ServiceNow. Do we have any questions for Alexander? Please come to the mic, or I can also give my mic to you. Just raise your hand.
Do you mean here or in the sorry, malice and agent land work, right?
Basically said defenses don't work.
Yeah.
I'm interested in like what things you tried.
Yeah. So we tried a few things. So these ones, this is Llama Firewall and Granite Guardian. I believe one is a observation filter. So it's essentially trying to remove malicious prompt injections from the observation. We tried that, but the main issue is that our triggers are super benign, right? It's just this information about the accessibility of websites. It says accessibility is very important, da, da, da. The real danger here is a statistical association between that trigger and malicious actions. So there's nothing in the observation that looks dangerous. So I think that's why they don't pick it up. And then there's another one. I think this is Llama Firewall, but we ask it, does this action make sense? Like, does this tool call make sense in the context of the user's goal? But very often, the action is just calling an API, and the guardrails really don't detect it, at least what we observe. We did get some success using GPT-5 as a defense, so it was able to defend in the WorkArena case. But it completely failed on the DRBench case because it was filtering pretty much everything because there were emails and phone numbers and stuff. So I think this shows that contextual guardrails are super important to work on.
I can also try to speak out loud if that's okay. So a question regarding the section right after BrowserGym, where you discussed how to train a browser agent and how to allocate the prompts properly.
Yeah.
I'm curious, I think you also mentioned that different
That's a really good question. I don't know exactly what this specific figure was for. So what we do, the flops that we count here in these charts, there's more in the paper, but they include the compute for the teacher to actually collect the traces and then the cost of fine-tuning on the traces. So I guess the bigger the observation, the more costly it is to train. So yeah, that's a great question. Probably you would be spending way more flops on training and data collection if you were using full DOM, for example, because it's just huge. If you were using screenshots, you have way less tokens. So I suppose with a fixed budget, you would spend less flop budget per iteration. But I can't tell you, but if you want, we can check offline afterwards.
Okay, maybe we can take one more question. Can you come to the mic, please?
If possible, I would like to ask 2 questions. The first one is, have you encountered any misclassification in your benchmark? And how much does it cost per minute per task for your model training?
Sorry, what do you call a misclassification in the benchmark?
So what if an agent is able to come up with a result that is correct, but is not identified as correct, false positive and false negative rate?
Okay, you mean did we put any mitigations in place to make sure we don't accept answers that are incorrect, but we would judge as correct? Is that what you mean?
Yes.
Okay, cool. So in WorkArena, one thing that is nice is we don't rely on judge models at all. This is all based on looking at the database state. So we will ask the agent, look, you need to order an Apple Watch, and then the way we validate the task is we go to the database and we check if the latest ordered item was actually an Apple Watch with the right settings. So yeah, I think for sure I cannot certify that there are no bugs or issues with validation, but I think it should not be a huge issue because we don't rely on automatic forms of judging for this benchmark. And you asked a question about compute, the cost of training. I don't know off the top of my head, but what I can tell you is that the experiments I showed on WorkArena level 3, the runs we did with GPT-5 cost about $200 USD to run on the full testing set with GPT-5. So this can give you an idea. I believe it's about 300 different tasks that we have in the test set.
All right. Please give a round of applause to Alexandre again, and then